Hey, this is Charlie Thompson, and this is the how-to video for Lab 7 Atmospheric Stability. In this video, I'm going to go over two examples of how to do the atmospheric stability problems. In this first example, we're going to simply take a parcel and lift it up through the atmosphere. And in the process of doing that, we're going to find the dew point temperature of the parcel. We're going to find the lifting condensation level of the parcel. If we find the dew point temperature, we're going to find the starting specific humidity. We're also going to find the final specific humidity because as the air cools, it's going to lose moisture to condensation, and then we're going to figure out how much water vapor condensed. So this question's based on actual conditions on Kauai, where orographic lifting produces some of the highest rainfall rates in the world, 486 inches a year. That's a lot of rain. That's over 40 feet. Well, 40 and a half, right? So what are we going to do? We're going to take a parcel of air from the Pacific Ocean at sea level to the summit of Mount Waialeale at 1,570 meters, which is 1.57 kilometers. Assume its temperature is 28 Celsius and has 98% relative humidity. And we're going to answer a bunch of questions. What's the initial specific humidity? What's the dew point temperature of the parcel? What's the parcel's lifting condensation level? What's the parcel's temperature at the summit? What's the specific humidity at the summit? And how many grams of water vapor condensed along the way? So we need the chart of maximum specific humidity. To calculate specific humidity, that is, well, in this case, we know the relative humidity is 95%. So what we need to do is find out what's the maximum specific humidity and then take 0.95 times that value. So maximum specific humidity at 28 Celsius is 24.3 degrees. I'm sorry, let me back that up. The maximum specific humidity for a parcel of air at 28 degrees off of the chart of maximum specific humidity is 24.3 grams of water vapor. 95% of that, so 0.95 times 24.3 is 23.1 grams per kilogram. So the initial specific humidity is 23.1 grams per kilogram. So then we take that 23.1 grams per kilogram, we look it up on the chart of maximum specific humidity, and we get a dew point temperature of 27 degrees. So the parcel's at 28. The dew point temperature is 27 degrees, so that's a difference of 1 degree, so it's going to have to go up 0.1 kilometers. The starting temperature minus the dew point temperature, 1 degree. Whatever the difference is between the starting temperature and the dew point temperature, you take that number, divide it by 10 to get the number of kilometers you have to lift it up to find the lifting condensation level. In this case, 0.1 kilometers. So what's the parcel's temperature at 1.57 kilometers? So the parcel is 27 degrees at 0.1 kilometers, and it's going to go from 0.1 to 1.57, so 1.47 kilometers of lifting. And as I'm doing this, I realize this is a bad example because the amount of lifting should be rounded to 1 decimal place. I wanted to use the actual value for the elevation of the summit of one of the wettest places on Earth. That's why we've got this. If this was given to you on the test, I wouldn't give it as 1 point. I would already have it in a form that you'd look at it and go, oh, he's already rounded it to 1 decimal place. So this would be 1.6 kilometers if I gave it to you on a test. But for today, let's keep going. So we're going from point 1 to point 0.1, the lifting condensation level was 0.1 kilometers, so going from 0.1 to 1.57 is a difference of 1.47 kilometers. The parcel's already cooled to dew point temperature, so it's going to cool at the moist rate of 6 degrees. So it's going to rise 1.47 kilometers and cool 6 degrees per kilometer for 8.8 degrees of cooling. The initial temperature at the lifting condensation level, not on the ground, but at the lifting condensation level was 27 degrees. 27 minus 8.8 is 18.2 degrees. So then if we know what its temperature is, we just go back to the maximum specific humidity chart. So given a temperature, a dew point temperature of 18.2 Celsius, which rounds to 18, the maximum specific humidity at 18 Celsius is 13.1 grams. And then we just have to find the difference, right? How many grams of water condensed from the surface up to 1,570 meters. So we started with 23.1, we finished with 13.1. That makes the math easy. So starting specific humidity minus the ending, 23.1 minus 13.1 is 10 grams of water vapor condensed. And that's it for that one. Now let's take a parcel and lift it up. I guess we're doing 3 examples, whatevs. So we want to find the dew point temperature again, the lifting condensation level, the final specific humidity, the grams of water vapor that condensed. We're going to use the environmental lapse rate to figure out the temperature of the atmosphere. And then we're going to find out, is the parcel stable? So what are we given? We have an air parcel at 35 Celsius with a specific humidity of 14.7 grams, 35 Celsius in the ground, ELR of 12. Answer the following questions if the parcel gets lifted to 4.5 kilometers. So now we know how high we're going. What's the dew point temperature, lifting condensation level, temperature of the parcel at 4.5 kilometers. Once we know the temperature, we can figure out what the specific humidity is. If we know the ELR, 12, we know what the temperature of the atmosphere is going to be. And then if we know the temperature of the parcel and the temperature of the atmosphere, we know if the parcel is going to be stable or unstable. So, given a specific humidity of 14.7 grams, we look on the chart, find the grams, slide over, and the dew point temperature is 20 Celsius. So given a dew point of 20 Celsius and a temperature of 35 degrees minus 20 degrees, so temperature minus dew point temperature equals 15 degrees divided by 10, because the dry rate is 10 degrees of cooling for every kilometer. So that's a lifting of 1.5 kilometers. We're starting at sea level. So the lifting condensation level is going to be 1.5 kilometers. So as the parcel rises, it's going to rise and cool at the dry rate till it gets to an elevation or an altitude of 1.5 kilometers. And then it's going to cool at the moist rate from 1.5 to 4 kilometers. Let's see what that looks like. So the parcel is 20 degrees at 1.5 kilometers. And it's going to go from 1.5 to 4.5, which is 3 kilometers of lifting, cooling 6 degrees per kilometer. It'll be 18 degrees cooler. It was 20. 20 minus 18 is 2 Celsius. Now we know the temperature of the parcel at 4.5 kilometers. Now we have to look up the specific humidity of the parcel. So the parcel temp is 2 Celsius, so the specific humidity is 4.4 grams of water per kilogram. The temperature of the atmosphere at 4.5 kilometers, well, the ELR is always given 12 Celsius, 12 Celsius degrees of cooling, 4.5 degrees of atmosphere going up through. 12 times 4.5 is 54 degrees cooler than the 35 Celsius we started with. That was the temperature of the ground, 35 Celsius. So 35 minus 54 degrees is negative 19 Celsius. So the atmosphere is negative 19. The parcel is 2 degrees. Is the parcel stable or unstable? Well, the parcel's 2 degrees. The air around it is negative 19. So the parcel is really unstable. Oh, now the third one. That was a surprise. So we're going to take a parcel, we're going to lift it up, and then it's going to sink. As it rises, as it goes up through the atmosphere, it's going to expand and cool. And when it drops back down and sinks, it's going to heat up. So now we have to find some more things. Dew point, lifting condensation level, final specific humidity of the parcel at the summit, grams of water vapor that we lost on the way, temperature of the atmosphere at the summit, and then is the parcel stable or unstable. We're then going to drop that parcel down and find the ending temperature, the specific humidity, and the relative humidity of the parcel. So this is mimicking the rain shadow effect. For example, on the east side of the Sierras, as the air goes up and over the Sierras, it expands, it cools, rain falls in the Sierras, but then on the east side, there's no rain left, so it's dry. All right, in this exercise, we'll take a parcel of air to the summit of Mount Rainier at 4.4 kilometers, then drop it down to Yakima at 300 meters above sea level. So, given an air parcel at sea level at 15 degrees Celsius with 40% relative humidity and an ELR of 7 degrees of cooling, answer the following. What is the dew point temperature of the parcel? So we're given the relative humidity and the temperature. So we look up 15 Celsius, find the max. The max is 10.6. The relative humidity is 40%. So 40% of 10.6 is 4.2 grams. So now we know the specific humidity of the parcel. If we know the specific humidity, we can look it up, and the dew point temperature is 1 degree. So we know the starting temperature, 15. We know the dew point temperature, 1 degree. 15 minus 1 is 14, divided by 10, because the dry rate is 10 degrees of cooling for every kilometer you go up. So 14 divided by 10, 1.4 kilometers is going to be the lifting condensation level. What's the temperature of the parcel going to be? Well, the parcel cooled to 1 degree at 1.4 kilometers. Then going from 1.4 to 4.4, that's 3 kilometers. It's going to be 18 degrees cooler. It was 1 degree at 1.4 kilometers. 1 minus 18 is negative 17 degrees. And then we just look it up on the maximum specific humidity chart and say, well, what's the maximum specific humidity at negative 17 degrees? 1.1 grams. That's what we have. To find the temperature of the atmosphere, we know what the temperature was on the ground, 15 Celsius, and we know what the ELR is, 7. So we're going from the surface 4.4 kilometers up, cooling 7 degrees at a time. So it's going to be 30.8 degrees cooler. The starting temperature was 15. 15 minus 30.8 is negative 15.8 Celsius. So the parcel is the atmosphere is negative 15.8. The parcel is negative 17. The parcel is cooler, so the parcel is stable. It's not going to rise anymore. The parcel is colder than the air around it. If the parcel sinks from 4.4 kilometers down to 0.3 kilometers, it'll heat up by 10 degrees per kilometer. So 4.4 to 0.3 is 4.1 kilometers of sinking times 10 degrees of heating is 41 degrees warmer. 41 degrees warmer than negative 17 is 24 Celsius. So what's the parcel's specific humidity? Well, the same as it was on the top of Mount Rainier. As the air sinks, it heats up, so it can hold more water, but it doesn't mean that it has any more water. For example, if you were in Las Vegas or Reno or on the other side of the Sierras, as that air is sinking, it's sinking in a desert, and it's not going to pick up any moisture because there's no moisture for it to pick up. The parcel's specific humidity then is 1.1 grams, although our parcel is now 24 Celsius, so the relative humidity will be really dry because the temperature went up and the specific humidity as the parcel rose dropped. So parcel specific humidity is 1.1 grams. As the parcel sinks, the parcel warms, but it doesn't get any more water vapor. The formula for relative humidity is specific humidity divided by max specific humidity times 100. The specific humidity is 1.1 grams. The maximum at a temperature of 24 Celsius is 18.9 grams. 1 over 18.9 is 0.058 times 100 works out to 5.8, and that's going to round to 6%. And that's it for the Lab 7 Atmospheric Stability How-To video. If you have any questions, please email me, please text me, please come to Zoom. I can pretty much guarantee 5-10 minutes of conversation will answer all of your questions and make this lab. It'll turn the lab from being a chore into being something that's less brutally difficult and maybe even entertaining. So, that's it for Lab 7. I wish you good luck this week.